2, module 3. And as you can see that the name under the wings of multivariate distribution, today I'm going to discuss marginal and conditional distribution with respect to certain problems for discrete pair of random variables, and as well as for bivariate random variables, I'm going to discuss the Bayes theorem. Bayes theorem has already been discussed earlier in module 1. Module 2 has its generalization for bivariate random variables. And today I'm going to go very slow because I'm not going to pressurize the students just before the examination of Monday, the tentative date of continuous evaluation test 1. And the syllabus, let me remind you, the syllabus of the syllabus of this examination will be just module 2 and module 3. That means you are going to study the hold on, let me check. You are going to study continuous random variable and their properties, distribution functions and densities, normal, exponential and gamma density, and along with that bivariate distributions and their properties, distributions of sums and quotients, conditional densities and Bayes rule. Now conditional densities, as conditional density and Bayes rule is there, and so therefore I'm going to finish my today's topic with that. Okay. Once I finish my today's topic, after that I'm not going to start anything new before the examination. So I wish you all the best for the exam. Now let us start. Let me save the chat once more. Okay. Today I'm going to discuss a few problems. First of all, the problems have all not been discussed earlier. In my earlier classes, I've discussed problems based upon continuous random variables. Here I'm going to discuss problems based on a discrete random variable. Now, I suggest all of you to keep a copy in front of you so that if rough work is needed, you can do it. Okay, so a little bit of rough work on your side will be helpful. And students, I must tell you one thing, and I also suggested the same thing in this morning session of EC section B, that although I'm sending you the notes, okay, these notes you are getting from Google Classroom, so, and we are all stuck up in this home environment, so please do not lose your ability to write. Okay, I will suggest you to write down all the things which are there in the note and make a fair copy of it. And if you do so, it will be a good practice, because if there are some minor mistakes, silly mistakes, which I am very much prone to sometimes, you can rectify it by yourself. And if the mistake is major, then you can show me that, sir, please rectify that kind of thing, that particular section of the note. Okay, so it will be a very good practice. So rest is up to you. My first problem, that is problem 1, is showing you a joint probability distribution for discrete random variables, a pair of discrete random variables x and y. Okay, and 1 by 8, half, 0, 1 by 4, 1 by 8, 0, these are all joint probabilities. And you see that the domain of the random variable x has two values only. One is -1 and one is +1. And the domain of the random variable capital Y has two values, -1, 0, and 1. I am supposed to find the marginal distribution of capital X, the marginal distribution of capital Y, the conditional distribution of capital X, given that capital Y is equal to -1. So I'm going to show you one by one how to calculate all this. You have already known the formula of marginal distribution of X in general sense. Okay, now here I'm going to calculate the marginal distribution of X when X is discrete and Y is discrete. Okay, so we shall apply the same formula, same rule, but remember that in discrete case, summation, the summation sign, the integration sign is replaced by the summation sign. Okay, let me show you the calculation. It's very easy, it's simple calculation, and this type of problems will be there in the examination. Now, I have again prepared the joint probability distribution as it is shown in the question. Okay, everything has been copied as it is, but two things have been added here. One extra column has been added and one extra row has been added. Try to recall the definition of marginal distribution of the random variable capital Y. Marginal distribution of the random variable capital Y is obtained when we take the sum of the values uh, on the basis of the values taken by the variable capital X. That means we take the summation of the joint probabilities, and the summation is taken over all possible values of X. Okay, that is that is defined as marginal distribution of the random variable Y. And marginal distribution of the random variable X is the sum of the joint probabilities, and the summation is taken over all possible values of Y. So I am when the case is discrete, we use the summation sign, and when the case is continuous, we use the integration sign. That is just a difference. Okay, that is how we distinguish between continuous and discrete case. The rest remains same. Now I'm going to calculate the marginal distributions or marginal probabilities of the random variable capital Y for each value of Y in its domain. So first of all, when Y takes the value -1, okay, we are adding these two figures 1 by 8 and half. That means what? We are taking the summation of the joint probabilities. Summation is taken over the values of X. Now when X equals to -1, the joint probability is 1 by 8. When X equal to 1, the joint probability is half. We are adding these two and we are getting 5 by 8. The first value of the marginal distribution of the random variable Y at Y equals to -1. Similarly, when Y equals to 0, we are adding the two probabilities 0 and 1 by 4. Okay, and we are getting the marginal distribution of Y for Y equals to 0 as 1 by 4. And when Y equals to 1, we are calculating the marginal distribution of capital Y as the sum of these two values, 1 by 8 at X equal to -1 and 1 and 0 when X equals to 1. So we are getting 1 by 8. Similarly, when we calculate the marginal probabilities of random variable X, we take the sum of these joint probabilities corresponding to each column. Okay, so what we do is that we take C. When we are calculating the marginal probability when X equal to -1, we are actually considering the joint probabilities for Y equals to -1, Y equal to 0 and Y equal to 1. Therefore, the definition, it is similar to the definition which I have already stated, that marginal distribution of the random variable capital X is the sum of the joint probabilities, and the summation is taken over all possible values of Y. So we are adding these figures and we are getting 1 by 4. And for X equal to 1, we are again getting the marginal probability of the random variable X, and that is 3 by 4 by adding these two terms. Okay. Now there is a beauty in this particular chart. The beauty is that you see when we take the sum of these marginal probabilities, marginal probability of Y and marginal probability of X, both these result in 1 individually. So summation Fyy is 1, summation Fxx is 1. So this if this comes, then you are pretty sure that your calculation is wrong. But if this is not coming, then there may be two things. If either your calculation is wrong, or probably we have made some kind of mistakes, or or probably some data are missing due to some reason or other. So this is a kind of checking criteria. So this completes the distribution chart, and which we call as marginal distribution chart for random variable capital X and random variable capital Y. Our next job is to find the conditional distribution of the random variable X given that capital Y takes the value -1. Now you see, to prepare this particular chart, what we have done is that we have retained the vector capital X, or the random variable capital X, with its possible values -1 and +1. Okay. And since we are going to define the conditional probability, we are going to find the conditional distribution corresponding to conditional distribution of x given capital Y equals to -1. So although y has three possible values like -1, 0, 1, I have only retained y equals to -1 here. I don't have to show other because it is not needed according to the problem. Now how to calculate this? Now students, if you can remember from my earlier class, that the conditional density of the variable x given that y is actually defined as, this is actually defined as, try to recall, is it is joint probability of joint probability value of x and y divided by marginal probability of y. Now we are going to the chart of joint probability. Joint probability of x, y at x equal to -1 and y equal to -1, from the chart it is 1 by 8. And the marginal probability of y at y equals to -1 is equal to 5 by 8. So we are dividing 1 by 8 by 5 by 8. And we're writing it as this. 1 by 8 divided by 5 by 8, which is equal to 1 by 5. Similarly, when x equal to 1 and y equals to -1, the joint probability is half, but the marginal probability of y is 5 by 8. So we are to find this particular cell value, we are dividing half by 5 by 8, which we have done over here. Half divided by 5 by 8. So the first result, the first conditional probability is coming out as 1 by 5, and the second conditional probability is coming out as 4 by 5. Okay, now here is another beauty. It is that if we add these two conditional probabilities, you are getting 1 again. 1 by 5 plus 4 by 5 is equal to 1. Now this problem is done. The problem has been selected from the exercise of joint point book. Okay, let us go to the next problem, problem number 2. It is also very interesting problem, although similar to the previous one. I have specifically selected this particular problem because to understand the Bayes theorem, this problem will be required. So you just be attentive and listen to me very carefully what I say. First of all, the joint probability distribution is given over here. Now, one thing, students, I must say to all of you that in previous class, I defined two terms. One is called conditional distribution and another is called conditional density. Distribution is synonymously known as chart or table. Here I have prepared the table, you see, with respect to x equal to -1 and 1 and y equals to -1. So this entire thing is called the conditional distribution. But these individual cell values are known as conditional density. So this is the difference between conditional distribution and conditional density. Probably you couldn't understand this from my earlier class when I defined it because that was theoretical. Since I'm today showing you the problem, so I'm distinguishing the two items, and probably you are understanding my point that the entire thing as a whole can be termed as a conditional distribution, but individual values in these cells are known as conditional density. Okay, now keeping this in mind, let us proceed. Joint probability this is the joint probability distribution chart, and these individual probabilities are joint probabilities. And you can remember this particular table because we have twice or thrice referred to this table in our earlier classes. I found this table by ourselves. Okay. So these are the joint probabilities, and the domain of x is now 0, 1, 2, and the domain of y is now 0, 1, 2. These are discrete points. Just like my previous problem, I'm going to calculate the marginal distribution of capital X and capital Y first. So what we do? We first, what I have done is that I have first copied the entire joint probability chart over here with an added column on the right hand side and with an added row to the below. The added column is giving you the values of the marginal distribution or marginal probabilities of the random variable capital Y, and the value fxx below gives you the marginal distribution of the random variable capital X, which is the sum of the joint probabilities running over all possible values of Y. So just like my previous problem, and you can calculate it by yourself, that I am adding the probabilities row wise. First of all, by adding these figures, I am getting 7 by 12. By adding these two items, I am getting 7 by 18. And since only one item is present here, 1 by 36, I'm writing here 1 by 36. All the empty cells will correspond to 0 probability. Empty cell will correspond to 0 probability. Similarly, to calculate the marginal probability of capital X, I'm taking the sum of this column, and that column. And you are getting respectively the values 15 by 36, half, and 1 by 12. Now, just like my previous example, if you add these three figures, you will get 1. So total marginal probability is supposed to be always 1. Total marginal probability of y is always supposed to be 1. Total marginal probability of x is always supposed to be 1. So 1 is being obtained over here, which indicates that my chart is complete. If you look at these marginal probability values as a whole, then you will say that it is a marginal distribution. But individual values like 7 by 12, 7 by 18, 1 by 36, 15 by 36, half, 1 by 12, these individual values are actually called marginal densities. This is the definition, that is the difference between distribution and densities. Then we are going to find conditional distribution, the conditional chart. Now, in my previous example, since I selected the problem from the book, and the condition given was y equals to -1, so we selected that value only. But if you are going to prepare the conditional distribution, then you have to consider all possible values of x and all possible values of y. Okay, just like we did in case of joint probabilities and marginal probabilities. So I have considered all possible values of x here and all possible values of y here. Okay, and what is the conditional distribution I'm calculating here? The conditional probability where capital X occurs given that capital Y has already occurred. And to calculate this, I am again applying the same formula which I applied above. It is the ratio of the joint probabilities to the marginal probability of the random variable capital Y. So what I am doing is that I am dividing 1 by 6 by 7 by 12, 1 by 3 by 7 by 12, 1 by 12 by 7 by 12. Then I am dividing 2 by 9 by 7 by 18, 1 by 6 by 7 by 18. Then I am dividing 1 by 36 by 1 by 36. But I am not dividing, okay, anyways, let me finish first. And in this way, by dividing each of these joint probabilities by corresponding marginal probability, I am getting these values: 2 by 7, 4 by 7, 1 by 7, 4 by 7, 3 by 7, and 1. And here also you see, if we take the sum total of all the marginal probabilities, you will find that the sum total is 1. 2 by 7, 4 by 7, 1 by 7. Take 7 as the LCM. And in the numerator, you are going to get 2 plus 4 plus 2. 2 plus 4 plus 1, that is 7. 7 by 7 is equal to 1. For the second case, I am getting 4 by 7 and 3 by 7. I'm adding these two figures, 4 plus 3 by 7, that is 7 by 7 equals to 1. And the last one is indeed itself 1. So all the conditional probabilities, okay, sum to 1. Now, entire chart is called conditional distribution chart for the random variable capital X given that random variable capital Y, and individual values 2 by 7, 4 by 7, 1 by 7, 4 by 7, 3 by 7, 1. These values are called conditional density. Those who are thinking that why haven't I divided 1 by 6 by 15 by 36, it is because I was preparing the table of f of x given y, and with the formula which goes like f of xy by fy. So that's why I was dividing by fy. But suppose I now ask you to prepare the chart of f of y given x, then by the conditional probabilities definition, it will be defined as f of xy by f of x. And then in that case, I'll divide 1 by 6 by 15 by 36, 2 by 9 by 15 by 36, and 1 by 36 by 15 by 36. You can try this particular problem. You can prepare this particular chart by your own after the class, okay, if you want to do so. Next comes the one interesting result is called it's not result, it is a definition. It is about independence of discrete random variables. Now, although I have written here discrete random variables, it is not like this definition is not true for continuous variable. It is also true for continuous variable. But since it is almost implied, so I have not actually, since today's my class is actually based upon discrete cases, so I have written here discrete random variables, but the proper representation could have been independence of the random variables. But the important part here is that we know, let me recall the definition of independent events. In independent events were defined in this way, that if capital A and capital B are two independent events, then probability of A intersection B is the product of probability of A and probability of B. Here, the thing is not exactly like that. It is something different. What is that? To define that, I have not actually considered here bivariate case. I have considered here the multivariate case, since n number of variables are present. Bivariate is a special kind of multivariate case. How am I defining this? Just to look at it. If f of x1, x2, dot, 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 xn is the value of the joint probability distribution of the discrete random variables, capital X1, x2, xn, at the point x1, x2, xn, and fi xi is the value of the marginal distribution of capital Xi at small xi for I equals to 1 to up to n, then the n random variables are independent if and only if f of x1, x2, xn is equal to f1, x1, f2, x2, dot, 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 fn, xn for all such points x1, x2, xn within their range. Important part is that if we have a joint probability like this for multivariate case, this joint probability function is being represented by f. Now these variables inside the function are the values of the random variable represented by capital, their caps. x1 is the value of x1, x2 is the value of x2, xn is the value of xn. This joint function, this joint probability density function, if can be represented as the product of individual the product of their individual marginal probabilities, like f1 x1, f2 x2, fn xn, then we will say that this function, these variables are actually of independent nature. Now, one interesting point is that the original function f here changes, and instead of that we are getting some other function like f1, f2, fn, and the values of these function at their respective points. Sorry, there is a mistake, it should be x2. Values of this function, values of this function at this point would be considered, and their product will be taken. If we can represent the joint probability by this, then we'll say that the random variables x1, x2, dot, 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 xn is a set of independent discrete random variables. If the x1, x2, xn are discrete, if they are continuous, then it will represent the independence of these continuous random variables. The entire thing will be clarified with the help of this beautiful problem, which has been selected from the exercise of John Font. I'm supposed to find whether the variables capital X, capital Y are independent or not, and their joint probability distribution is given in this particular manner. These colored figures are representing the pairs of variables. So gray colored items here represent the pair of variables -1 and 1. Blue colored items represent the pair of variables -1 and 1. This is -1 and -1, that is -1 and 1. The green colored represent the pair of variables 1 and -1, and the yellow colored represent the variable 1 and 1. So, and you see, according to the question, for each of these pairs, the distribution has value 1/4. So I have to prepare the chart. So what I have done, I have put the range of x over here, which is -1 and 1 according to the question. I have put the domain of x. I have put the domain of y over here, which is -1 and 1 also. And all the probabilities have been written like this. 1 by 4, 1 by 4, 1 by 4, 1 by 4, as it is given. The joint probabilities are same for all the pair of values. Then I have calculated the marginal probabilities. Marginal probabilities, you already know how to calculate. Marginal probability of y for y equal to -1 has been calculated as the sum of 1 by 4 and 1 by 4, that is half. Marginal probability of this is half. Marginal probability corresponding to x equal to -1 is half, and marginal probability corresponding to +1 is also half. Now, according to the definition, if I can represent the joint probability of xy as the as product of some function of the marginal probabilities of x and y, then we can say this particular pair of random variables are independent. Now you see, if we select this value x equal to this particular row where the marginal probability is half, and this particular row where our marginal probability is half, then this particular column, then the value corresponding to this row and that column, their product half into half will represent this 1 by 4. If we consider this column and that row, then the product half and half will represent 1 by 4, the joint probability of this cell. If we consider half and this half, their product will represent the joint probability of this cell. And if we consider half and half, their joint probabilities, their product will represent the joint probability of this cell. So what does it imply? This is implying that this joint probabilities fxy can be represented as the product of the individual marginal probabilities, and therefore this pair of variable x and y are random independent in nature. Okay, this problem is also there in the exercise of joint point. Now let us come to the last part of our today's class. It is called Bayes theorem for probability densities. Okay, now what is that? Now try to recall the Bayes theorem which we studied in module 1. The Bayes theorem goes like this. If you can recall that if capital A and capital B be two events, then not necessarily independent, then probability of A given B can be represented as probability of A intersection B by probability of B by the definition of conditional probability, and this can also in turn be represented as a probability of B given A into PA by PB. So P of A given B is related to P of B given A and vice versa, and therefore Bayes theorem is also termed as the theorem of inverse probability. Here the thing is, although the notation is kind of similar, but calculation will be a kind of something different. Not a huge difference is there, but you just pay attention, you will understand. I have considered two random variables, capital X and capital Y, not necessarily independent, because you know if the variables are independent, then Bayes theorem collapses. So if capital X and capital Y are two joint random variables, then f of x given y and f of y given x are conditional densities. These are the notations. I am only using the notation of the functions. Okay, f of x given y and f of y given x represent the conditional densities of the variables of type capital X given capital Y and capital Y given capital X. And suppose f of xy represent the joint probability of the random variable of type xy. And similarly, fx and fy represent the the marginal probabilities of the random variable capital X and capital Y respectively. Then the conditional density, conditional probability f of x given y can be represented as f of xy by fy is equal to f of y by x into fx by fy. See, the structure is similar to our known definition of the theorem of inverse probability. Okay, here f of x given y is related to f of y given x, and therefore it is a case of inverse probability. And similarly, you can find also, you can write this particular probability also in terms of f of x given y to calculate f of y given x. Okay, the other result has not been shown over here, but it is automatically implied. We are going to understand this calculation with the help of the following example. So what I have done is that I have pasted here the two tables which I have already calculated above. The first table represents the joint probability distribution along with the marginal probabilities, and the second table represents the conditional probability of the type x given y. Okay, so I am going to calculate here this particular function. I am going to calculate f of y given x at the point x equal to 1 and y equal to 0. Okay, so let us see how to calculate this. We shall take help from the above table. To calculate the conditional probability of y given x at the point x equal to 1 and y equal to 0, I have first written the formula with the help of the joint probability and the marginal probability. So I have written f of xy at the point x equal to 1 and y equal to 0 divided by marginal probability of x. See, marginal probability of x, and since fx is the univariate, so here I have written only x equal to 1. This is similar to, by definition, f of x given y, because on the left hand side we have y, f of y given x. It is f of x given y at the point x equal to 1 and y equal to 0 multiplied by the marginal probability of f of y, fy at y equal to 0, because it is also univariate, divided by the same thing. I'm going to show you how to calculate this conditional probability first by taking this example, this particular form, and then by taking this particular form. And I'm going to show you that these two forms are similar, for which I'm going to take the help from the above chart. First of all, let us consider this first definition. Now you see, when x equal to 1, let me scroll up a little bit. You see, when x equal to 1, capital X equal to 1 and y equal to 0, that means here small x equal to 1 and small y equals to 0. In this case, for according to these two paired, this particular pair, the probability is 1/3. The joint probability is 1/3. So I have written here 1/3, and the conditional probability, the marginal probability of x at x equal to 1, you go to this chart, when x equal to 1, the marginal probability is half. Okay, so I'm putting here half, and the result is coming out as 2/3. Now I'm using this particular formula. To calculate the conditional probability of y by x, we are using this value, these values from the chart. F of x given y at x equal to 1 and y equal to 0. To obtain this particular value, we are considering this particular chart. Okay, now for x equal to 1 and y equal to 0, the corresponding conditional probability is 4/7. Okay, and the marginal probability of y at y equal to 0, the marginal probability of y at y equal to 0 is, come back to this chart, this is the marginal probability section. At y equal to 0, the marginal probability is 7/12. So I'm multiplying 4/7 by 7/12. Don't try to look for marginal probability in this particular chart. Marginal probabilities are present in joint probability chart. Okay, divided by marginal probability of x at x equal to 1. And for this, I'm again considering this column x equal to 1, and the corresponding marginal probability is half. Now I'm multiplying and dividing the things. 4/7 into 7/12 gives you 4/12, that is 1/3, and divided by half, so we are getting 2/3. So if we apply both the results, we are getting the same conditional probability. So these are conditional. This value 2/3 is called the conditional density of y given x. Now it is only one value at x equal to 1 and y equal to 0. In this manner, you can prepare the entire chart, conditional distribution chart for the random variable of the form y given x. Okay, for which you are going to consider all possible pairs of values of capital X and capital Y. I have shown only one calculation. You can try and find the entire chart of f of y by x accordingly by using the definition of the theorem of inverse probability. Okay, so in this particular manner, this Bayes theorem is defined for this bivariate case. Now, if we keep on increasing in mathematics, we always try to generalize things, and if you keep on increasing the number of variables, okay, and the problems of the kind where the more than one variables, more than two variables are required, the Bayes theorem, the marginal probabilities, the conditional densities, the joint probabilities will be similarly defined. Okay, so in today's class we have learned the three important parts. One is how to apply uh, the concept of marginal and conditional distribution for discrete random variables, and what is the difference between the definition of independence of random variables in case of bivariate case and univariate case. And also we have learned the form of Bayes theorem for bivariate case. Okay, so with this I'm going to conclude my topics of module 3. Module 3 is finished with Bayes rule. Okay, and now my part is over. Then here comes your part. You are supposed to practice the problems from the book which I'm referring, or any other book which you find suitable to your choice, and you are going to solve problems. Now, I understand that probably we are moving a little bit faster. I am moving a little bit faster because you see today there is a board of director meetings, and your coordinator called me to know how much syllabus I have finished. Now I told her that I have finished 50% of the syllabus because 3 modules have been finished uh, today. So therefore the management, the authorities, and gradually the WBT will ask for every details, students marks, percentage of the absentees list, the percentage of attendance, everything. So I am moving a little bit faster, but my suggestion that you go along with your favorable pace. Okay, but since the examination is knocking at the door, I am taking the continuous evaluation test 1 on Monday. So for the time being, you forget everything about module 1. You concentrate. You have got 3 days, uh, uh, including today. So you just concentrate on these 2 modules, module 2 and module 3. You do sums on continuous random variables and their properties, distribution functions and their densities, normal, exponential, and gamma density, bivariate distribution and their properties, distribution of sums and quotients, conditional densities, and Bayes rule. And I shall set easy questions. You don't have to worry for that. And you have already scored good marks in quiz test. You are going to keep that form of yours in the upcoming examination. So I wish you best of luck. And with this, I'm going to conclude my today's session. And today the total number of students present is 34, and I have saved all of your chats, and I'm going to send the absentee list to the CR. Okay.